Hi NET aspirants, our part number 2 based on the topic sets, function and groups. Especially I have selected all the questions from group. Without wasting time, number 1, prove that the set 1, 2, 4, 5, 7, 8 under the modulo 9 multiplication is a group. We have given a set that is 1, 2, 4, 5, 7, 8. Modulo 9 under multiplication. We have to prove that it's modulo 9 under multiplication, it's a group. What is the science behind these numbers? They all numbers are less than 9. Number 1, all numbers are less than 9. Second, they are all relatively prime. They have no common factor with the 9 except 1. They have no common factor with 9. Either 1 and 9 common factor is 1. 9 2 common factor is 1. 9 4 common factor is 1. 9 5 common factor is 1. 9 7 common factor is 1. 9 8 common factor is 1. They are relatively prime to each other and they are less than 9. It is the science behind choosing these numbers. 9 multiplication, we have 1, 2. Let me construct the case table. 1, 2, 5, 7, 8. 1, 2, 4, 5, 7, and 8. 1 is the identity. Multiplication with 1. Do not alter anything. 1, 2, 4, 5, 7, 8. Let's see from where our game starts. 1 to the 2. 2 times 2, 4. 2 times 4, 8. 2 times 5. 2 times 5, 10. 2 times 5, 10. Anything greater than 9, subtract 9 from it. We will get 1. Write 1 here. 2, 5 the 10. 2, 5 the 10. The quantity is greater than 9. Subtract 9 to get anything under 9. To get anything under 9, that's what. Same. 2, 7 the 14. 14 is the quantity greater than 9. Subtract 9. You will get 5. Here, 2 8 the 16. 2 8 the 16. Subtract 9. You will get 7. That is the technique behind making this, constructing this table. Similarly, 4. 4 1 the 4. 4 to the 8. 4 4 the 16. 16 means 16 minus 9 will get 7. 4 5 the 20. 20 subtract 9. Again 9. Still I will get 11. Again subtract 9. Till you get some number less than 9. Till keep on subtracting 9 till you get a number that's less than 9. So here remainder is 2 in that case. Modulo 2. Here 4 7 the 20. 8. Keep on subtracting 9, 9, 9, 27, and the remainder is 1. 1 is our answer. 4 8 the 30. 2. 4 8 the 32. Keep on subtracting 9, 9, 9, 3 times. It's 27. 3 and 2. Here is 5. Similarly, multiplication with 5, it will become 5. 5 to the 10. 10 means 1 because 10 minus 9 is 1. Here 4 5 the 20. 20 means 2 9 the 18. 20 minus 18 is 2. 5 5 the 25. 5 5 the 25. 1 9 the 9. 2 9 the 18. 25 minus 18, we will get 7. 5 7 the 35. 35, keep on applying table of 9. 9. 5 7 the 35. 35, let me write here 35 minus 27. I will get how much? 15 minus 7, 8. 8 is the answer in that case. What about here? We are making this 5 8 the 40. 5 8 the 40. 9 4 the 36. 40 minus 36. 40 minus 36, we will get 4. Nothing repeats. Nothing repeats. No entry is 2 times. No entry is 2 times. That is the validity to check. 1 7 the 7. 2 7 the 14. 14 is the quantity greater than 9. 14 is a quantity greater than 9. Subtract 9 from 14, you will get 5. 14 minus 9, you will get how much? 1, and it's 5. Okay. Now again, 7 for the 28. 28 minus 27, I will get 1. 7 5 the 35. 35 means 35. 35 it is 8. It will give me 8. Again, 7 7 the 49. 7 7 the 49. Keep on applying table of 9. 9 4 the 36. 9 5 the 45. 9 5 the 45. You will get 4. I will get 4. Here, 7 8 the 56. 7 8 the 56. 56. Keep on subtracting. 5 9 the 45. 5 9 the 45. 5 10 the 50. 5 10 the 50. But there's modulo 9. 9 5 the 45. I will get 1. 11. Still subtract 9. I will get 2. That's mine too. Similarly, the column of 8 to be completed. 1 8 the 8. It's mine 8. 2 8 the 16. 2 8 the 16. 16 minus 9 is my 7. 8 for the 32. 32 minus 27. 32 minus 27. I will get 5. 8 5 the 40. 40 minus 36. I will get 4. 8 7 the 56. 8 7 the 56. I will get 2. 8 8 the 64. 8 8 the 64. 7 9 the 63. 7 9 the 63. Minus 63 is R1. That is the way to construct the modulo table of 9 under multiplication. What is the logic behind selecting these numbers? Take all numbers that are below 9, under 9, and they are relatively prime to 9. We haven't written 3. We haven't written 6 because they have common factor 3. These are the numbers. They share 1 as a common factor with 9. They are known as relatively prime. It is logic of modulo 9. Keep on multiplying ordinarily. Keep on multiplying ordinarily. Anything greater than 9. Anything greater than 9. Keep on subtracting 9 or multiple of 9. Keep on subtracting 9 or multiple of 9 till you get a number less than 9. Till a number you will get less than 9 from these numbers and construct the table. How? Here 1 is the identity. 1 is the identity. I can show you inverse of each element. Here is 2. Keep on traveling horizontally to get 1. This is 2. I am finding the inverse of 2. I am finding the inverse of 2. I am traveling horizontally to get 1. I have got 1. With whom number it has been multiplied? 5. 2 5 the 2 5 the 10. 2 5 the 10. 2 5 the 10. 10 minus 9 1. 2 minus 9 1. So inverse of 2 is 5 and inverse of 5 is 2 according to modulo 9. Inverse of 2 is 5 and inverse of 5 is 2 according to modulo 9 because their multiplication will give us 1. Their multiplication will give us a 2 5 the 10. 10 is a number greater than 9. Subtract 9, I will get 1. Okay, cool. What is inverse of 4? Keep on traveling horizontally to get 1. We have got 1 here. And what about travel vertically? Travel vertically, I will find 7. 4 7 the 28. 4 7 the 28. Keep on subtracting 9, 9, 9. I will get 1. I will get 1. So 4 times 7 according to modulo 9, I will get 1. So inverse of 7 is 4. Inverse of 7 is 4 and inverse of 7 is 4 and vice versa. They are inverse of each other. They are inverse of each other. What about 5? Keep on traveling horizontally to find 1. Then keep on traveling vertically. You will get the number 10. 5 to the 10. We have already done this. 5 and 2. Here 7 we have already done. 7 and 4 inverse of each other. What about 8? Let's see 8. Keep on traveling in the column of 8. I will get 1. Keep on traveling. First, keep on traveling horizontally. I will get 1 in the column of 8. 8 is here. 8 is here. That's the column of 8. Keep on traveling 8, 8. I will get this one. I'll get this. So inverse of 8 is 8 in that case. Inverse of 8 is 8. 8 and 8 is 64. 64 means subtract 63 because 63 is a multiple of 9. 63 is a multiple of 9. Keep on subtracting 9, 9, 9, 7 times. 7 times the 63 to get 1. So inverse of 8 is 8. Inverse of 8 is 8. These are the inverse. Inverse of 2 is 5. And inverse of 5 is 2. Inverse of 4 is 7. And inverse of 7 is 4. Inverse of 8 is 8. And inverse of 8 is 8. And inverse of 1 is 1 according to definition of identity. It also satisfies your associative law. It is closed. It has unique inverse of each element and has identity, so it is a group under multiplication of modulo 9, as well as it is a abelian group, it will give you same result when multiply a with b or b with a with b or b with a. Moving towards next question. Next question is a simple one. I am moving towards question number 3. Then we come to question number second letter. It's a tiny one to explain. We keep our tempo to attempt good questions, heavy questions, standard questions. In case of abstract algebra or group theory, these are simple numbers, but at having good standard. We have given some matrices here. Show that form a group under matrix multiplication. We have operation is 1. We have given identity I, A, B and C. I, A, B and C. Same situation, same story, same saga continues. I with I, we know that one. I with I times A is A, I times B is B, I times C is C. Everybody is familiar. This is our identity under multiplication. It works as a one like numbers. 1 is multiplied with any quantity, it will give same result. In the same token, multiply 1 0 0 1 with any 2 by 2 matrix, you will get the same. Now A with I, it's A times A, what happens? Let's see and find out. What is our A? 1 0 0 minus 1 multiplied with 1 0 0 minus 1. A with A, let's see what is our result. 1 times 1 is 1, 0 times 0 is 0, 1 times 0 is 0, this is also 0. Multiplication of 2 by 2 matrices. 0 plus 0, 0 times 0 is 0, minus 1 times 1 is positive 1. So we have 1 0 0 1. Means if multiply A with A, I will get I. A with A, I will get I. Similarly, if I multiply A with B, mine A is 1 0 0 minus 1. This is our A. What about B? We have minus 1 0 0 1. Multiply them. 1 times minus 1 plus 0, same. 0 plus 0 here, it's 0 0 0 and it's our minus 1. We will get minus 1 0 0 minus 1. Is there any matrix having this? It's equal to C. This is our C. We will get C. Same now. A multiplies with C. A multiply with C. A times C. What is our A? Our A is 1 0 0 minus 1. That's our A. Multiply with C. That is minus 1 0 0 minus 1. It will become minus 1 plus 0. I will get 0 plus 0. Here it's 0 plus 0. That is our 0 1 times 1. We have something like minus 1 0 0 1. Minus 1 0 0 1. That's the value of B. It's equal to B. It's equal to B. Cool. Look at this. Nothing repeats. A, I, C, B. Order changes, nothing repeats. Order changing, nothing repeats. Then B with I will get B. B times A. B times A. Let me erase this and find B cross A. Make the case table. The result of multiplication of all these 4 matrices comes within these 4, not outside the 4. Now I have B times A. What is our B? Minus 1, 0, 0, 1. Or A, B times A. 1, 0, 0, minus 1. Minus 1 plus 0. That's our 0 plus 0. It's 0. 0 times 1, 0, 1 times 0, 0. That is 0 times 0, 1 times minus 1 is minus 1. We will get minus 1, 0, 0, minus 1. It's equal to what? It's equal to C. It's equal to C. So B times A is R C. B times B, let's see and find out. P is R minus 1, 0, 0 minus 1, 0, 0, 1 with minus 1, 0, 0, 1. It will become positive 1 plus 0, 0 plus 0. Again 0 plus 0 and we have 0 plus 1. We are going to get identity 1, 0, 0, 1. That's equal to our identity. That's equal to our identity. The next result will be A. The next result will be A. Let me prove for you as well. B times C. B times C. What is mine B? Mine B is minus 1, 0, 0, 1. What is our C? Our C is minus 1, 0, 0, minus 1. Multiply. Minus 1 times 1, positive 1. Plus 0. At 0, it's also 0. 0 times minus 1, 0. 1 times 0 is 0. 0 plus 1 times minus 1 is minus 1. So we are going to get 1, 0, 0, minus 1. 1, 0, 0, minus 1. It's equal to what? A. That's our A. That's our A. Column 1, 2, 3. Column 4 is missing. C times I is C. C times A. What props up? Let's see and find out. C times A. Our C is minus 1, 0, 0, minus 1. That's our C. C times A. 1, 0, 0, minus 1. That's our minus 1 plus 0. Similarly, 0 minus 1 times 1, it's minus 1. 0 times 0 is our 0. Then minus 1 times 0 is my 0. 0 times minus 1 is our 0. 0 times 1, 0. Minus 1 times 0, 0. 0 times 0 is 0. Minus 1 times minus 1, it's plus 1. I will get minus 1, 0, 0, 1. It's equal to B. It's equal to B. So C times A is our B. C times B, let's see and find out. Minus 1, 0. 0 minus 1, that's mine. C. C with B. C with B, our B is, that's minus 1, 0, 0, 1. How much? Positive 1. It's 0. So 0 and it's minus 1. I hope you are familiar by the multiplication of 2 by 2 matrices. 1, 0, 0, minus 1. It's equal to A. So we have A. Now C times C. What props up? Let's see and find out. C times C. C times C. It's also C. Minus 1, 0, 0, minus 1. Surely it's going to be identity. Surely it's going to be identity. Let's see and find out. Minus 1 times 1, minus 1. 0 times 0, it's our 0. Minus 1 times 0, it's also 0. 0 times minus 1, it's also 0. So 0 plus 0. 0 times 0 is 0. Minus 1 times 1 is 1. 1, 0, 0, 1. Sorry, it's our identity. It's our I. It's our I. Cool. Everything's, every element, every product, every result of every product comes from IABC. IABC. It shows that it is closed under matrix multiplication. It shows that it is closed under matrix multiplication. Binary operation has been satisfied. Binary operation has been satisfied. Similarly, one can take 3 elements to verify associative law. Let's find out what about inverse. Here, I have I. Keep on moving to get I. In numbers, we have identity 1 under multiplication, 0 under addition. 1 is the identity under multiplication of numbers. 0 is the additive identity under addition. Here it is a matrix multiplication. Under matrix, we have identity 1, 0, 0, 1, the unit matrix. I have A, keep on traveling in horizontal direction I, then start moving with traveling in vertical direction A. A times A times A, I get I. It shows that A is equal to A inverse. A is equal to A inverse. It's invertible matrix. A is equal to A inverse. Similarly, if I want to find the inverse of B, keep on traveling horizontally to get I, then here B times B is I. So B is equal to B inverse. B is the self inverse of this one. What about C? Keep on traveling in horizontal direction, then in vertical. So C times C is our identity. So C is equal to C inverse. Every element is inverse of itself. Every element is inverse of itself. Every element is inverse of itself in that case. Inverse of A is A, inverse of B is B, inverse of C is C. So it is closed. It satisfies associative property. It has inverse. It has inverse of A is A, inverse of B is B, inverse of C is C, and they are unique. And we have identity 1001. So it is a group under multiplication. We have showed that. Moving towards next question. Moving towards next question. And we are almost through the frame. Next question, we have given some complex functions. Complex function, they are how they are defined. Let's see and find out. Identity function, I z of z is equal to z. It's known as identity function. We have formula f of z is equal to minus z, and furthermore g of z is equal to 1 over z, and h of z is equal to minus 1 over z, where z is not equal to 0. Z is not non-zero complex number. Non-zero complex number. Let's construct a table for them to prove that they are closed under the composition of the functions. It's closed under the composition of functions. Later then find identity. It is the identity. Let me prove as well. Find the inverse of f of z, g of z, h of z, and vice versa. Composition of function. Let me write here. Composition of function. Let me write. So okay. Composition of function. Okay, I have I, F, G, and H. I, F, G, and H. Composition with identity element will give us the same result. I, F, G, and H. One can prove. Now F times I, it's F. F times F. What happens? Let's see. FOF. F of Fz. F of z is equal to minus z. It means that in the function of f, instead of z, insert plug in minus z. It is given by minus, value of z is negative z. It will become positive z. So f of minus, so FOF, so our FOF is going to be z, and z is equal to identity. So I will give identity. It proves that f is inverse of itself. F is inverse of itself. Why? Because composition of f and f results in I. Results in I, or one can write FOF, it results in z. It results in z. What about this? F times g. Composition of f and g. F and g. We have f of g of z. F, value of g of z is 1 over z. It means that in the function of f, plug in z, plug in 1 upon z instead of z, plug in 1 upon z instead of z. F of z is equal to z. Instead of z, we have to plug in 1 over z. So its fog is equal to 1 over z, which is equal to, in return, it is equal to g. It's equal to g means f times g is rg. Then composition of f with h. F with h. F with h, h of z. H of z is equal to minus 1 over z. It's equal to minus 1 over z. It shows that plug in instead of z in the function of f minus 1 over z. F is minus, f of z is minus, instead of z, that we write 1 over z. Negative, negative, positive, it's equal to 1 over z, which is equal to g in return. Which is equal to g in return here. G repeats in that case. Let me check. F times H. There is F H of Z. H of Z is minus 1 over Z. With F minus plus, I will get G. It's okay, correct. Repetition is also possible in that case because whatever the result is, just we are writing. Nothing goes beyond this I, F, G, and H. What about the G, I? It's G. G with F. Go. F of Z is equal to minus G, and G is defined in return as 1 over, instead of Z we have to insert minus Z. It will become minus 1 over Z. It is in return, it is equal to H of Z. It is equal to H of Z. So it's equal to S. G times G, GOG, G of Z is equal to 1 over Z. It shows that instead of Z we have to plug in 1 over Z. It will become Z. In return it is equal to I. It's equal to I. Now G with H. G with H finally. Composition of G of H of Z. G or H of Z is minus 1 over Z. Okay, cool. In return G is 1 over negative 1 over Z. It will become GOH is will become minus Z. Minus Z is equal to F. It's equal to F means G composition H is equal to F. Nothing repeats in that case. What about H? H times I, H times F. Composition of H with F. Composition of H with F. Oof. Composition of H F of Z. H F of Z means minus Z. F of Z is minus Z. H of Z is equal to, it is equal to minus 1 over the minus 1 over, instead of Z we have plug in minus Z. Minus plus, it's equal to 1 over Z, which is equal to G of Z in return. Means H times G, H times F is G. H times F is G. Then H times G. Composition of H with G. H Hawk. Composition of H with Z. Composition of H with G. H G of Z is equal to how much? 1 over Z. Then H, it's equal to negative 1 over Z. It or H O G will result in minus Z, which is equal to F of Z in return. So H times G is equal to F. Now H times H, what happens? Let's see and find out. Composition of H with H. H of Z is equal to minus 1 over Z. It means minus 1 over minus 1 over Z. Minus plus, it will become Z. Z means I. Z means I. It's equal to I. It's equal to I. Here, just F repeats. Let me check these two elements. Then might be there is a mistake or error I have committed. Might be. F times G. Composition of F G of Z. G of Z is equal to 1 over Z. G of Z is equal to 1 over Z. F means instead of Z I have to plug in minus 1 over Z, which is equal to minus 1 over Z is equal to H of Z. So F times G. F times G is H. It's mine H. Now everything settled down. Now let me verify F times H as well. Composition of F H of Z. F H of Z is equal to minus 1 over Z. It's equal to minus, instead of Z I have to write minus 1 over Z. Minus plus 1 over Z. 1 over Z is equal to G. It's correct. Now our table is 100% correct. IFGH, FIHG, nothing repeats because there is a repetition of G 2 times. I have checked the element. F times G is my H. I have written G as a mistake. So it is close. Why? Because the composition of I, F, G and H comes within IFGH. Nothing goes out, nothing goes beyond, nothing goes beyond. It shows that it is it is closed with respect to the composition of the functions. Next, I is our identity because I times F we get F composition of I F F. Composition of I G same G. Composition of I H is H. I of Z is equal to Z. It works as a one like number or like a matrix. When it is multiplied with any number, you will get same number. It is if it is multiplied with any matrix of 2 by 2, you will get the same matrix. In the same token, I of Z has been multiplied, means if we find the composition of any function with I of Z, we will get the same function, we will get the same function, we will get the same function as in the first. Second, now let's find about inverse. Here comes F, keep on moving horizontally, that's I. It shows that F times F, we will get I. It shows that F is inverse of each other. It's a self-inverse of each other. Similarly, G, keep on moving horizontally, then vertically. We have composition of G with G is equal to, it shows that G is equal to G inverse, they are self-inverse. What about H? Keep on traveling. H times H, I get I, it shows that H is inverse of itself. H is inverse of itself. Easily one can show by taking three elements, finding the three functions, taking their composition, you will get the same results as in the case of associative law. First GH, then with F, or first F and G, then with H, you will get the same result. You will get the same. It proves that it is a function. In that case, it is also a commutative function as well. Let's see. F G, we will get H. What about G F? We will get H. They are commutative as well. One can verify. Moving towards fifth question, and second I have missed on purpose because it's a tiny question to be dealt later. Now show that the set G2 raised k where k belongs to integers, Z stand for xylene, set of integers in our subcontinent, otherwise it has been denoted by I for integers. It is a group under multiplication. It is a group under multiplication. Taking any two elements, 2 times k1, multiply k1, it's k2. They are in multiplication, add their powers. Look at this. The composition of the multiplication of any two numbers of this type result again in that type. So it shows that it also belongs to our set denoted by G. So it is closed or it is closed under multiplication of numbers, ordinary numbers, closed under multiplication. Okay, how to satisfy associative law? 2 times k1 times 2 raised k2 times 2 raised k3. I am taking three numbers is equal to 2 raised k1 times 2 raised k2 times 2 raised k3. In that case, solving this bracket first, it will become 2 raised k plus 1 k2 times 2 raised k3. It is tantamount to 2 raised k plus 1, k plus 2, k plus 3, k plus 3, sorry. Similarly, on the right hand side, 2 power k plus 1 is 2 times k2 plus k3. Again, this is the same, add their powers, it will become k1 plus k2 plus k3. So associative law has been verified. Associative law has been verified. What about identity? Identity. 2 raised 0 means 1. 1 also belongs here. 1 can be written as 2 power 0 form, where 0 belongs to integers. It has the identity as well. Now let's check inverse. Inverse is also present. Inverse is also present in that case. What is the inverse of 2 raised k1? The inverse of 2 raised k1 is negative k1. 2 raised negative k1. Inverse of 2 raised minus k2 is 2 raised positive k2. Each element has inverse because we have plus minus 1, plus minus 2, plus minus 3, plus minus 4, and so on, and so on. Inverse of 2 raised a is 2 raised negative a. Inverse of 2 raised negative b is 2 raised positive b. Each element has inverse, it's unique, it's closed, it has identity, and it also satisfies commutative property. 2 raised a times 2 raised b is equal to 2 raised b times 2 raised a. It will become 2 raised a plus b is equal to 2 raised b plus a. Here, in case of integers, a plus b is equal to b plus a. In case of integers, a plus b is equal to b plus a. It's commutative. Addition of Addition of integers is commutative. So it's a group as well as it is a group under multiplication as well as it is a commutative group. It also satisfies the fifth property as well. It has identity. It is closed. Every element has inverse, and inverse is unique. And inverse is unique. Finally, the second question that we have left on purpose. Let's see and find out. If is z set of integers, we have binary operation. Binary operation, it is given to us. How it has been defined? A circle B always results in 0. A circle B always results in B, where for all AB belongs to Z. AB belongs to Z. Take any integers, write this operation here. You will get, suppose I am writing the integers as A, A1, A2, A3, A4, and so on. Similarly, okay, plus minus A, plus minus, plus minus, and so on. Similarly, A1, plus minus, it's not 0. It is the operation defined in that fashion. It is given to us. A1, A2, plus minus, A3, plus minus, A4, and so on. Now, if we take any two elements, A1 closed under the given operation, A2 always results in 0. It's 0, 0, 0, 0, 0, 0, always 0. Every entry is 0 in that case because it is given to us, or binary operation is defined in that fashion. So 0 also belongs to integers. It is closed. It is closed. Closure property has been satisfied. Closure property has been satisfied. What about identity? Identity in that case, how to find identity? Let's see and find out. It's closed under the given binary operation. Whatever is given to us, we have to follow this. I have taken integers plus minus a plus minus a2. I haven't written plus minus 1 plus minus 2 plus minus 2 to look ordinary, some standard, or one can write 0 plus minus 1 plus minus 2 plus minus 3 and so on. Keep on adding. Whenever you operate them according to the given binary operation, a circle B always results in 0. A circle B always results in 0. Always results in 0. Take any two elements, operate according to this operation, the result is 0, so it is closed. Why? Because 0 belongs to integers. Because 0 belongs to integers. What about other properties? Let's see and find out. Our identity is given by, definition of identity is A star E is equal to A. A star E is equal to A. In that case, A star E is equal to A star E is equal to, according to this, A is A or B is E. We will get 0. 0 is equal to A. So we are going nowhere. We are going nowhere. We are not in a position to find identity. We are not in a position to find identity because definition of identity is A star E or E, whatever the operation is given to us, A circle E given binary operation E or E given binary operation A always results in A. Always results in A. What about this? Its results in 0. Its results in 0 is equal to A. So we are not in a position to define E properly. E properly. Number 1, E does not belongs to Z. Even Z vanishes. E vanishes. We are not in a position to find E. What about inverse? Inverse is unique. Inverse is unique. A star A dash is equal to A dash binary operation given A They all results in zero. They all results in zero. We are not in a position to find inverse. Are taking two different inverses, A it's equal to E and B inverse of A is A dash and inverse of A dash is A. If we operate them, this it is equal to 0, it's also equal to 0. So their inverses are not used. Their inverses are not unique because inverse of every element is 0. Every element binary operation results in 0. No, we are not in a position to define E properly. We can find E. Second, inverses are not unique. Inverses are not unique. Inverses are not unique. Inverse of A dash is 0, B dash is 0, C dash is 0. And according to the definition of group, inverse is always unique. Inverse is unique. That is not the case in our question. Inverse is unique. In that case, it is not the case. Second, we are not in a position to find identity. We are not in a position to find identity. To prove a group, we have to apply four conditions. Always stuck to it. Always stuck to it. Work within that parameters, and you are going to work for this. A star B belongs to G for all AB belongs to G. This is known as closure property. Some writer call it binary operation. Number one. Number two, associative property. It states that A star B star C is equal to A star B, A star B, A star B bracket B star C. It means that first you have to operate AB then with C. In that case, you have to start from left, extreme left. In that case, you have to start from extreme right, extreme right. First BC then with A. It's equal. In case of associative law. Number third, identity A star E or E star A always results in A, where E is identity. E is identity. Number four, inverse is unique. A dash or A dash star A always results in E, where A dash is the inverse of E. Inverse, inverse of E. All these are the four requirements for a group. In that case, we are not in a position to find identity. Identity fails. Identity fails. We are not in a position to find identity. Second, inverse is not unique. Inverse is not unique. Inverse is not unique. That's why it is not a group. It is not a group. It's my tiny effort to quench your thirst to about groups. It is a mind boggler type topic for the students. I have tried my best to open this up. It's all by itself. Next.